Before I get started, I want to thank the Epidel event coordinators for scheduling this video competition. I want to thank Kutztown University of Pennsylvania for the wonderful research opportunities they've given me. And most importantly, I want to thank Dr. Ju Zhou for working with me over the past year to research graph theory. And specifically, we were researching something called unique efficient dominating sets. But before we can discuss that, let's first touch on the idea of domination. So here I have a path of 4 vertices, and we'll specifically look at this vertex right here. We say that a vertex dominates itself and the vertices to which it is adjacent. So in this example, this vertex dominates itself, it dominates this vertex, and it dominates this vertex. Another way of saying this is that a vertex dominates all of the vertices in its closed neighborhood. So once we have the idea of domination, we can talk about dominating sets. When I circle a vertex, that means we're placing it inside of a set. We'll circle this vertex and also this vertex. A dominating set is a subset of the vertices of a graph such that every vertex is dominated by one of the vertices in the dominating set. Here, we do have a dominating set. This vertex is dominated by this one, this vertex is dominated by itself, this vertex is dominated by itself, and this vertex is dominated by this vertex. Dominating sets in and of themselves aren't remarkably interesting. However, things get really fun when we start to impose certain restrictions on our dominating sets. From dominating sets, we move on to efficient dominating sets. An efficient dominating set is a dominating set in which every vertex is dominated only once. Here, this vertex is only dominated by this vertex, so we're good. Here is where we run into problems. This vertex is dominated by itself and by this vertex, so we don't have an efficient dominating set. We can fix that. Instead of circling this vertex, we will circle this vertex right here. Now, this vertex is only dominated by itself, so we're good. However, we now run into problems with this vertex. It's dominated by this one and by this one, so we have to fix that also. Instead of circling this vertex, we'll circle that one. Now we have an efficient dominating set. This one is only dominated by itself, this one is only dominated by this one is only dominated by this one, and this one is only dominated by itself. Once we have the idea of efficient dominating set, we then move on to what Dr. Zhou and I have been researching, which is unique efficient dominating sets. A unique efficient dominating set refers to when a graph only has one efficient dominating set. A path of 4 vertices has a bunch of different dominating sets. However, this is its only efficient dominating set. Hence, it is a unique efficient dominating set. And Dr. Zhou and I have been coming up with complete characterizations of particular types of graphs, such as trees, grids, caterpillars, spider graphs, figuring out criteria to determine which of those do and don't have unique efficient dominating sets. And in order to do that, one of the tools that we used is coming up with certain operations. Basically, we have 2 small graphs with unique efficient dominating sets. How many ways can we combine them into a larger graph that also has a unique efficient dominating set? Here's one of the operations that Dr. Zhou and I came up with. Let's say we have 2 graphs. Each of them has a unique efficient dominating set, such as 2 paths with 4 vertices. We will choose 2 vertices that are not in the unique efficient dominating set, and we'll connect them with an edge. This larger graph also has a unique efficient dominating set. Now, this result was used a lot by Dr. Zhou and myself. However, it's not remarkably self-evident, so I want to spend the remainder of my presentation showing how we proved this. In order to prove it, we have 2 graphs, G1 and G2. And we know that G1 and G2 both have unique efficient dominating sets. We'll call them D1 and D2. And we're choosing two vertices that are not in D1 and D2. We'll call those V1 and V2. And we're connecting them with an edge. Here's what we know. We know that we already have one efficient dominating set. We'll call it D. And D is the union of D1 and D2. The question now becomes, is D unique? And that's where we're going to focus our proof. We're going to suppose that we can create a different efficient dominating set called D prime. And logically, there are four cases, and those four cases center around V1 and V2. Those four cases are V1 and V2 are both in D prime, V1 is in D prime, V2 is in D prime, or neither V1 nor V2 are in D prime. We'll start with the first case. The first case is that V1 and V2 are both in D prime. Well, here we already get a contradiction because we have two circled vertices next to each other, so D prime is not an efficient dominating set. So case 1 leads to a contradiction. Now we'll move on to case 2 and case 3. Now case 2 and case 3 are logically the same. Case 2 is that V1 is in D prime, case 3 is that V2 is in D prime, so we'll just do case 2 without loss of generality. V1 is in D prime. Here's how we get our contradiction. Notice that because V1 is in D prime, there's no way that any of the vertices in G2 can dominate any of the vertices in G1. Hence, G1 has to dominate its own vertices. But we've just proven that there's only one way to do that. D1. In other words, D prime union G1 is equal to D1. This is one of the premises of our proof, that D1 is the unique efficient dominating set of G1. But we get a contradiction because V1 is not in D1. When we chose our two vertices, we explicitly chose two vertices that are not in the unique efficient dominating sets. So V1 is not in D1, but here, since it's circled, we're saying that it is in D1. Contradiction. So case 1, case 2, and case 3 all lead to contradictions, which forces case 4. Neither V1 nor V2 are in D prime. In order to get a contradiction here, we use a very similar thought process. Since V1 is not circled, none of the vertices in G1 can dominate any of the vertices in G2. And since V2 is not circled, none of the vertices in G2 can dominate the vertices in G1. So G1 has to dominate its own vertices, and G2 has to dominate its own vertices. And there's only one way to do that, via D1 and V2. Hence, not only is the union of D prime and G1 equal to D1, but the union of D prime and G2 is equal to D2, which furthermore means that D prime is the union of D1 and D2. However, that's just our original D. So D prime is not a different efficient dominating set, it's just equal to D. Contradiction. When we tried to make a different efficient dominating set, we just ended up making the same one. So cases 1, 2, 3, and 4 all lead to contradictions. Hence, not only is D an efficient dominating set, D is a unique efficient dominating set. And using this operation and a lot of others, Dr. Zhou and I found these to be very powerful tools in proving that larger and more general graphs have unique efficient dominating sets.